or you've attempted to create your own carbon cycle. We're going to talk about the carbon cycle. Understanding how carbon is moving in and out of different Earth spheres is very important to understanding on how the greenhouse effect works and understanding the current climate change that we are in. So we already talked about this once, but I'm going to cover it again just so you guys kind of have a refresher of your memory. These are all different ways that carbon can get into our atmosphere. We've got burning of biological matter. That could be forests, that could be grasslands, that could be anything that is living, any holding tank of carbon. We have dead and decaying matter that's sitting inside of lakes and swamps and ponds that are releasing methane into the air. And then we have these carbonate rocks, rocks that were formed at the bottom of the ocean of dead and decaying organisms and sediments from the ocean floor. Once they come up to the surface, they are reacted with the slightly acidic rain, which causes them to release some of their carbonate rock into the form of oxygen and carbon into the atmosphere. Now, this photo is an example of fossil fuel burning. Now, it looks really bad. It looks like toxic in this photo, honestly. But what we're actually seeing here is this factory is creating and generating power, and then they use these smokestacks is sort of allowing some of that stuff to sort of burn off. So we're seeing a little bit of soot here. Soot is just basically some of the carbon that didn't burn off properly. We're seeing a little bit of toxins here. I mean, not great to have toxins, but we're seeing a little bit of toxins. And we're not actually seeing CO2. Carbon dioxide is coming off in this picture, but carbon dioxide is an invisible gas. So we're really not seeing carbon dioxide here. What we're mostly seeing here is water vapor. So we're seeing large clouds that eventually will evaporate. If there was this much pollution coming out of smokestacks all the time, we wouldn't have air that we could breathe, honestly. So yeah, most of this is actually water vapor. But if you remember, water vapor is also a greenhouse gas. In fact, it's the strongest greenhouse gas, and it's responsible for about 80 to 90% of the heat retention that we have due to the greenhouse effect. All right, dead and decaying matter. This is an example of a rotting cow. Here, this cow is giving off methane as it rots. It's giving off carbon dioxide, and it's also leaking juices and other minerals back into the soil. This is an example of volcanism. Volcanism also allows carbon dioxide to get in the air, and as well, the two main gases of volcanic eruptions are water vapor, as water vapor being number one, and then carbon dioxide being number two. Cows, because of the food that we feed them, because we feed them a lot of grains and oats, and, well, oats are grains, things like wheat and corn, things that aren't their natural food, they actually end up producing a lot of gas. And this gas that they produce is methane. And if you remember, methane is better at retaining heat than carbon dioxide is. It's actually a very potent greenhouse gas. So there's actually some suggestion that people stop eating so much red meat, stop eating so much cow meat, because it's causing, raising of cows is causing an alteration of our climate. It's causing an increase in the climate, its temperature. Now, there have been some recent studies showing cows that are fed grass, that are out in a pasture, tend to actually have a carbon, what we call carbon neutral. They're actually not adding more than they're taking out in different processes by fertilizing the grasses, and the grass is growing stronger. So maybe, we're not sure just yet, but it may be if we just stop feeding them things that they're not supposed to be eating, that maybe they wouldn't be belching and burping so much methane into the atmosphere. Alright, so carbon also exits the atmosphere in certain ways. Now this is actually not underwater, but this is another example of a limestone. Limestone forms at the bottom of large lakes and oceans, where dead and decaying organisms sink to the bottom of the ocean, and then they form this layer of ooze, and then eventually it solidifies into rock once those sedimentary layers get compressed enough over time. Now the way that stuff gets into the ocean is this stuff here. it rains down into the ocean. So rain not only helps clear and clean the pollution out of the sky, but it also dissolves a lot of this stuff called CO2. CO2 will dissolve in the rainwater and it will rain down to the ocean, where organisms living in the ocean will be able to use that to create food in their body structure. Those organisms are photosynthetic. And then we have that carbon taken out of the air. Now, organisms can also fall into lakes and swamps that have a limited amount of oxygen, and it can form this sedimentary rock, which is called coal. This is the stuff that we're burning into the atmosphere. It's kind of nasty stuff, but this is what we're burning for a lot of our electricity in the United States. Whoops. No, 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 no. Alright, now remember that there's only a couple ways that that carbon, sorry, sometimes Prezi just doesn't like to play along, so how that carbon actually leaves the atmosphere. One of these ways is through photosynthesis. That's one of the biggest ways that the carbon leaves the atmosphere and actually enters the biosphere. Right, let's go ahead, getting ahead of myself. So the largest reservoir for carbon is right here, the rock. Most of all the carbon on the planet is locked away inside of rock. The second largest reservoir, the second largest carbon sink is what we call it, because it sinks into the ocean out of the sky, is the ocean. Let's go ahead and diagram that now. Turn to the page of your notes where you have a spot to create a diagram. Okay, we're going to go ahead and draw a carbon cycle for your notes. So you're going to be on the page of your notes where there's a spot for that. Now I would turn your paper sideways to be able to fit it properly, or you can draw it vertical if you want, but I would definitely turn your page horizontal if I were you. So what we're going to do is you're going to go ahead and draw along with me. Is you're going to draw a land surface, and then you're going to dip down to the lowland, and that lowland area is going to turn into our ocean surface. Okay, now we're going to draw a few features on our diagram. The first feature is going to be a volcano. And our volcano is going to erupt gases into the atmosphere. So here we're going to have, we're going to call this volcanism. And we're going to have arrows showing the movement of carbon. So anytime we have arrows on our diagram, they're not pointing to a label or something like that, but they're going to show the movement of the carbon out of our volcano and into the atmosphere. And remember, the atmosphere means the air. Okay. So the next thing I'm going to go ahead and draw is we have other ways that the carbon is going to get into the air. And one of those ways is through the weathering of carbonate rocks. Now these are not rocks from the volcano. Rocks from volcanoes are typically mainly of basalt. These are rocks that were formed once in the bottom of large lakes or the ocean, and they are made up of a chemical called carbonate, carbon with 3 oxygen atoms. When the rain in the sky rains down, it's always slightly acidic, and it's slightly acidic actually because of carbon dioxide. Carbon dioxide dissolves into the rain, and it allows carbon to come out of the air. And as it does, it actually rains down on these carbonate rocks, and it will release carbon from these rocks into the air in a process called weathering. Now when this rain rains down into the ocean, it's going to allow for little organisms, algae that's growing all over the surface of the ocean. We're going to have kelp forests growing underwater. We're going to have seagrasses on the seabed. All of those photosynthesizing organisms, they need to get carbon, and the way they do it is the rain will bring it down, and so we'll actually have carbon coming out, going into the ocean, and this process will be photosynthesis. These organisms will also be respiring, as well as fish that are surviving on these organisms. And so as they respire, they're taking in carbon dioxide. Well, they're taking in food and oxygen, and they're giving off carbon dioxide and water vapor. And so they will respire. So we call that respiration. All right, now those organisms will die, especially the plankton. We got a lot of plankton, and they'll float down to the bottom where their dead and decaying and rotting bodies will form a layer of something we actually called ooze. You don't need to know that term, but it's actually called ooze. And over time, after we get more and more of these layers, we'll have a layer of carbon that's solidifying into rock. So we have this stuff going down to the bottom, and we call this rock formation. And it's actually forming with that chemical carbonate. So for these rocks to ever become weathered and release their carbon to the atmosphere, they have to be uplifted and brought up to the surface where they're going to be affected by rainwater. Now, one of the reasons why they don't dissolve in the ocean is because the ocean is actually alkaline or basic, while the rain is going to be slightly acidic. The acid will dissolve the rocks, and then the basic conditions will allow the rock to be forming down here. All right, we're still missing a lot of features. So one of those features is going to be photosynthesis of organisms on land, and we're going to be having burning of fossil fuels, and we're going to have burning of forests as well. So over here in my drawing, let me go ahead and move this over a little bit. Over here in my drawing, I'm going to go ahead and draw me a road, just because I can. And on this road, I have a car. Thank you, Mara. Go away. That's my German Shepherd. She's trying to help. All right, and my car burns fossil fuels, and as it does, it releases those hydrocarbons. Once they burn them, they burn the hydrocarbons and allow... sorry, my cat's coming to help too. It releases water vapor and carbon dioxide. So when we burn fossil fuels, we will release into the air those substances, so releasing carbon dioxide in the air. So this is called burning of fossil fuels. Okay, now let's go ahead and get our forests on here. I'm gonna draw myself some trunks. And then I'm gonna put some treetops on top of those. Okay, thank you for shading the whole entire drawing. Move, cat. Okay, so our forest is going to be absorbing carbon dioxide from the atmosphere in, again, the process of photosynthesis. So photosynthesis, they're absorbing carbon dioxide from the atmosphere into the plants themselves and making things like sugar and lignin to make, lignin, part of their bodies. Now, we also have the trees respiring because they eat the food they make as well. That's how they live. And that process just like the process of the organisms in the ocean, is called respiration. So that's respiration. And then if our forest were happen to catch on fire, let's say one of my trees here is catching on fire. That's what this orange thing is. Sure, this flame is fire. That will take that stored carbon that's in the forest, in the trees, in the plants, and it will return it to the atmosphere. And this process is burning of forests. All right, let me check here, make sure we got everything. We got burning of fossil fuels. We've got volcanism, we've got photosynthesis, we've got respiration, we have burning of forests, we've got weathering. We're missing one thing. One thing we're missing here on is decay. When things die, we call it decay. So let's go ahead and, sure, we'll put someone died at a dead body on the side of the road. And we know they're dead because, of course, they have X's for their face, for their eyes. All right, so this person's dying. As they're dying, they're rotting. And we have carbon eking into the ground and some juicy stuff. And we have carbon that's eking into the air in the form of carbon dioxide and methane. And we call this process decay. All right, and that is our carbon cycle. Now, you're going to have to be able to get a diagram on the next assessment. The next assessment is going to be after spring break. But you're going to have to recognize all these different things. So you're going to be given a carbon cycle. And say rock formation will be here, but there will be a blank for you to write the word that goes there. You'll be given all the words on this chart. You're just going to have to put them where they go and try to identify all these different processes. So make sure you study it, at least in Longhorn Pride, on the day that we have this assessment, and that you're ready and prepared and know how carbon moves throughout Earth systems, so that you can also understand the process of chemical cycling of carbon in Earth systems. And we're going to talk about how burning fossil fuels is actually contributing to climate change. And we're going to try to talk about how we know that the climate change that we're currently going through can be attributed to our burning of fossil fuels. So burning of fossil fuels, first of all, they're called hydrocarbons. Hydro means hydrogen, and carbon means, well, that one's easy, it means carbon. So basically, these fossil fuels are made up of hydrogen and carbon bonding. When we burn them, it combines with oxygen and it creates carbon dioxide, puts the oxygen with the carbon and oxygen with the hydrogen, and actually also makes carbon dioxide and water vapor. When you burn fossil fuels, you're giving off carbon dioxide and water vapor. Now, both of these compounds are greenhouse gases that we're adding to the atmosphere. When we burn these in the atmosphere, we're putting more of this carbon into the air. And when we have more carbon dioxide, we have more water vapor in the air, we're going to be warming the planet. We're going to be retaining more of that heat from the sun that comes in and making it have a harder time escaping to space. Now, a lot of that carbon that goes up into the air, that excess carbon that we put into the air, is absorbed by organisms. It's absorbed by trees. It's absorbed by, most of it's actually absorbed by the oceans and taken in by ocean organisms. Carbon dioxide is awesome for plants. Remember we talked the other day, carbon dioxide is the reason why we have bread, reason why we have actually milk as well. It's the reason why we have all the food that we have on our planet. Most of our food, now I'm thinking about it, I think all of our food has to have carbon dioxide as that base to be able to form. So without that, we wouldn't have any food to eat. Without it, we wouldn't have trees photosynthesizing. We wouldn't have plankton photosynthesizing, giving us oxygen to breathe. So carbon dioxide is a vital ingredient to life here on Earth. You are a carbon life form. Without carbon dioxide, you would also not exist. So a lot of people like to call carbon dioxide a pollutant, and a lot of people are trying to get it registered as a pollutant so that it can be regulated like other pollutants are. But as far as the state of Utah is concerned, carbon dioxide is a beneficial gas. It's just maybe not beneficial in large quantities. So as far as we're concerned, we don't call it a pollutant in our state at least. Now, how does the burning of fossil fuels also add to pollution? We're not talking about carbon dioxide, we're talking about pollution with burning of fossil fuels. The things about fossil fuels is they're not just hydrocarbons. They've got a lot of bad things mixed in with the fossil fuels. Now, coal is the absolute worst. It's got a lot of nasty stuff in it, a lot of sulfur. You can actually see bands of yellow that run through some pieces of coal where you can see the sulfur. You've got nitrogen compounds running through there. And when we burn those things, we add that junk to the air. All right, so it's here it says fossil fuels aren't just hydrocarbons. When we burn them, we can produce the non-pollutants like water and carbon dioxide. But then we also produce toxic pollutants like soot, which is just basically particles, solid particles of unburned material that go into the air and go into your lungs. They exacerbate asthma and any kind of lung conditions that people have. It creates carbon monoxide when it doesn't burn very efficiently. We create nitrogen and sulfur compounds in the air. Now let's talk about why these things are bad. And actually, it is not here, but we actually also add in, by burning coal especially, mercury to the atmosphere. Mercury is a neurotoxin. It blocks your body's ability to sort of communicate. It goes into your brain. If you get enough of it, it will kill you, and you will get mercury poisoning. But another big reason why mercury increase in the atmosphere is so bad that it's getting into our fish, it's getting into our food. And if a woman who's pregnant eats enough mercury by accident, it will cause her baby to have permanent birth defects. It will cause her baby to have mental retardation, and it's not a good thing. Let's talk about carbon monoxide. Carbon monoxide is not carbon dioxide. Carbon monoxide is a carbon and one oxygen bonded together. And when you breathe that in, you can't smell it, you can't taste it, you can't see it. But what it does is it binds to the hemoglobin, which is part of your red blood cells, that helps you have oxygen absorbed from your lungs. So it kind of, in a way, slowly suffocates you to death because it binds to that hemoglobin and it doesn't let go. It kind of takes the place of oxygen and doesn't allow oxygen to fill that void. So basically, slowly, over time, if you get too much carbon monoxide, you'll pass out, you'll get delirious, you don't know what's going on, and then you can actually die from this stuff. Nitrogen and sulfur compounds, when they combine with oxygen in the air, they turn into nitrous oxide, which when dissolved in water will become nitric acid and nitrous acid. Sulfur will become sulfuric acid, and both of these components are cause for acid rain. Before I said that rainwater was slightly acidic. That's from carbon dissolving in there, turning into carbonic acid, but it doesn't really make the rainwater acidic enough to be acid rain. It's just slightly acidic. This stuff, nitrogen and sulfur compounds, they make the rain very, very acidic and very, very dangerous for plants. It can destroy crops, it can kill trees, it can cause immunity deficiencies with people. So it's all around not good stuff. So carbon dioxide rates have been increasing. Before the Industrial Revolution, they were at about 280 parts per million. Now this thing, parts per million, this means for every 1 million molecules that are in the air, 280 of them would be carbon dioxide. That's not very much. Carbon dioxide, remember, only makes up 0.04% of our entire atmosphere. It really is not that much stuff in our atmosphere. But this is one of the ways that we know or that we suspect humans are increasing the carbon dioxide in the atmosphere. So before 1790, we had a pretty stable level of carbon dioxide at 280 parts per million. Well, if I pull up this graph, if it lets me pull up this graph, so I'm right-clicking, right here, we have concentration of of carbon dioxide here. And then here we've got time on the x-axis. And it's going up from 1750, 1800, 1850, 1900, all the way up to 2000. Now here, about here is the Industrial Revolution. This orange line represents the concentration of carbon dioxide in the atmosphere, and then it has this little uptick. Here, this blue line is called anthropogenic emissions, meaning anthro meaning, remember, man, and pogenic meaning created. Here, this is basically what we know we've burned into the atmosphere. So some of that has come out. A lot of what we burned on the atmosphere has come out. But here, this is the graph of how much we've been burning. In the Industrial Revolution, we started burning a lot, and we are burning more and more and more fossil fuels every single day. But what's remarkable about this is you can see the atmospheric concentration goes up with the amount of CO2 that people are burning in the atmosphere. So this might just be coincidence. It's not, probably. But here it does show a good relationship between these two factors. Now here's another graph of atmospheric CO2, 1960 to about 2018 here, I'm estimating. Here, this data, we see this red line that goes up and down, up and down, and up and down. But what we see in the overall trend of the data is carbon dioxide levels are definitely increasing. According to this graph, this is a current graph, it's about 408 parts per million. Now remember, pre-industrial levels, 280 parts per million. And now here in today we have about 408. Oh my gosh. If I could learn how to use a computer. All right, now you remember these graphs. These are our Milankovitch cycle graphs that we use. Remember, this is going all the way from present day back in the past 400,000 years. Remember that time frame, 400,000 years. Not 400 years, 400,000 years. And we see this cyclical pattern, this high temperature, dropping down, cold temperatures, high temperature, cold temperature, and it moves in lockstep with carbon dioxide emissions. This is also has sea level on this one, but that's irrelevant right now. So we've got global temperatures are high, carbon dioxide is high. When global temperatures is low, carbon dioxide is low. And it moves in this lockstep pattern because of those Milankovitch cycles. Every about 100,000 years, we've got a warming period, we have a cooling period. We have a warming period, we have a cooling period. We have a warming period, cooling period. Now here is why scientists are so concerned. Now everybody's not really paying attention to the presentation. I want you to look up right now. Carbon dioxide concentrations moving up and down, and then here is today. This is how this graph is different than the ones we looked at before. Here is our carbon dioxide concentrations today. This is why scientists are so freaked out. The temperature is going to take a while to start warming up as we retain more and more every single day. But look at how much more carbon dioxide emissions we have. Look how high this spike is compared to the spikes in the past. Look at the spike here. And so we're kind of terrified of what's going to happen to this temperature spike when we start retaining more heat than we can handle and that we can get rid of on planet Earth. All right, so you don't need to write that down, sorry. And actually, that's information we already talked about. CO2 levels are high. All right, so here's another thing. How can we really tell, though, that carbon dioxide is from fossil fuel usage? How do we know that that's not coming from a volcano? How do we know that we just haven't had more volcanic action lately? Well, first, we know we haven't had more volcanic action on the planet. We can see that. Volcanoes give out and pump out a projected about 2% of the amount of fossil fuels that people burn into the air. Even having that fact, we can deal with something called the carbon-14 isotopes. Now this is kind of complicated, so try to pay attention. When we have volcanic eruptions erupting into the air, it's going to be increasing carbon dioxide levels. Now we talked about the oxygen isotope and showed how when we use the mud cores, we could take the ratio of oxygen 16 and oxygen 18, and that helped tell us what the temperatures of the ocean were based on those different ratios of those isotopes. Well, we do something kind of similar with carbon 14. Carbon 14 is radioactive. It decays over time. And so basically, carbon 14 is a stable form of carbon, and carbon 14 is not. And when carbon 14 is unstable over long periods of time, I think it's like 5,000 years, it will decay into carbon 12. Not all of it, some of it. Basically, it has a half-life, but I'm not going to explain half-lives right now because that's been more complicated than a video is going to explain to you. So, over time, carbon 14 decays into carbon 12. When we have volcanic eruptions, we have a higher ratio of this radioactive carbon 14 to carbon 12. Both of them come out of the volcano. However, fossil fuels are old. They're millions of years old. And the carbon 14 that used to exist in these fossil fuels, almost all of it has decayed. Almost all of it has changed from carbon 14 to carbon 12. And when we look at the air in the atmosphere, when we take samples of it and we look down at that atomic level, what we're seeing is very few molecules of carbon 14, and we're seeing a lot more of carbon 12. And every year, that ratio of carbon 12 gets bigger and bigger and bigger. We start having more and more of carbon 12, more of this old carbon, this carbon that has decayed over time. So when we look and examine the carbon dioxide that's in the atmosphere, we can see that it's come from fossil fuels. It's like a fingerprint telling us this is where this carbon has come from. All right, let's go ahead and take notes on that. Now remember, make sure you pause if I'm going too fast. I'm sure I already have gone fast in this presentation. I'm sorry for that, but write this down. So this is how we know that the carbon actually is coming from burning of fossil fuels. First, fossil fuels has very, very old carbon, mostly lacking that newer radioactive carbon 14. Next, the carbon that exists in the atmosphere has a much higher ratio of carbon 12 to its radioactive cousin isotope carbon 14 than it should. Next, this is indicating that much of the carbon in the air is actually from that older carbon. That's that older carbon that actually comes from fossil fuels. All right, lastly, the excess or extra carbon dioxide that is in the atmosphere nearly equals the amount of excess of the fossil fuels that we burned. So we know how much we've dug out of the ground, we know how much we've burned, and we look at the amounts, there's not more carbon dioxide in the air than we burned. Again, pause. I'm going to go ahead and move on. So pause if you're not done writing. All right, so who's authority? Who really knows? If we look at the American public, and this changes every year, more people are starting to see that global warming is not a myth or global warming is not some kind of lie. But right now, 70% of American public agree that global warming is happening and that it exists, and that global warming is doing harm to the planet. as well as it's doing harm to human populations. Now, not all of those people believe it's man-caused, that it's caused by humans, but 70% of the United States now agree that global warming is a thing. If we look at politicians, that number is a lot lower, which is kind of weird. You would think that politicians would mirror what the American public think, but only 54% of Republicans think that global warming is a thing, while 76% of Democrats do. Now, this is always an argument against climate change. They would say, not all scientists agree. Not all scientists believe in this global warming thing. Well, they kind of do. So we've had a lot of consensus on the census. If we look at global warming experts, climatologists who actually study climatology, and they're studying the climate, and they're studying paleoclimates, and they're seeing all this stuff. If we look at those people who have created papers, who've done research on the matter, 97 out of 100 climate experts agree that humans are causing global warming. 97. So here we've got that all these people, 97 of them, believe that we have global warming and that's man-caused. Now, like, what is those 3%? What do the 3% know? They must know something else. Here's what the 3% here. These two people that are shaded in gray, they represent the 2% of all of these 100% of scientists that think global warming is a thing, but maybe it's not man-caused. So here we've got 99% of scientists that study this area believe that global warming is a thing. And now this one red represents the 1% of scientists who think we are not headed for global warming. They think that we are in global cooling, or that we think that we're not doing anything, that's just stasis, or they think that we're just in a period of a little bit of warming and it's just a natural fluctuations. So of all the 100% of scientists that study this, we actually only have 1% of them who don't think that global warming is a thing. So when you have a lot of people trying to dispel global warming and saying, oh, that's not true, or it does not exist, our scientists don't even agree on it. Scientists do. The studies definitely show that they definitely do, and people who say otherwise are just trying to lie and trying to deceive people. Alright, I'm going to guess we don't have time for this video, so I'm going to go ahead and stop the video now, and we will start this video again when we get back from spring break.